Hi everybody and welcome to our talk. I am Tom Horweg from the Interactive Media Lab Dresden, and together with Philipp Berger from the University of Rostock, we will present our work on responsive matrix cells. Philipp and I are joint first authors and worked on this project together with Heidi Schumann, Raimund Dachselt and Christian Tominski. With our investigations, we aim to facilitate working with multivariate graphs. These graphs are a challenging data type, as both structural and multivariate aspects are of interest at the same time, besides the traditional challenges of graph visualizations. This means an analyst needs to see how nodes are connected, but also how node attributes are characterized. Even further, the links themselves can also be detailed with attribute values. Importantly, the visualization should be able to provide an overview on the network, for example, allowing to see clusters or outliers. But also it needs to reveal the details for specific regions of interest. Finally, support for editing the graph is often desired as well, but rarely possible within the same tool. Of course, we are not the first that aim to address these challenges. There's a notable body of work on how to visualize multivariate networks out there. Here, Nobre et al.'s recent state-of-the-art article or Karen and colleagues' book are providing good overviews. However, the existing solutions are often optimized for one certain aspect, for example, showing the structure, or the multivariate aspects, or revealing the specifics of one particular dataset. Our goal is to provide a more flexible solution by following a focus and context approach for a matrix visualization. More specifically, inspired by Berger and colleagues' work, we start with a combined similarity and adjacency matrix. In this matrix, we then allow for creating multiple focus regions where embedded responsive visualizations are provided in the corresponding cells. Within these, analysts can explore the details, but also make use of integrated editing facilities. So let's have a look at the matrix itself. It consists of two parts, the adjacency part and the similarity part. The adjacency part is the bottom left, showing if an edge exists between two nodes as well as its weight. This allows analysts to recognize structural patterns, such as clusters or hubs, as well as identifying links with strong or weak connections. The top right part shows the attribute-based node similarities for each node pair, thus a calculated measure such as the Euclidean distance across all node attributes. A dark green encoding means that two nodes are very similar, and red that they are quite different. This also allows to discover groups with similar nodes or outstanding nodes. So the combination of both parts addresses the challenge of providing an overview on both structure and attributes of the network. Of course, for all dimension patterns, it must be supported to sort the matrix accordingly to make them visible. For the identified regions of interest, analysts can then use the responsive matrix cells to reveal the details via embedded visualizations. These embedded visualizations behave responsively and can adapt to different aspects. First of all, the part in which a selection is made defines the what is shown. This is either node or edge attributes. The visualizations can be embedded in two ways, either in the individual cells, called unit cells, or in a meta cell that spans the selected cells. The what and where also imply what needs to be visualized, so either one, two, or n objects. In consequence, this affects which specific visualization techniques are suited. For example, consider a unit cell in the adjacency part. The visualization would have to represent one specific edge with its attributes. In contrast, a unit cell in the similarity part would represent the attributes of two nodes at the same time, providing a one-to-one comparison. Finally, a meta cell will always represent n objects, so either n nodes or n edges. The flexibility of our approach also involves an adjustable level of detail of the cells. They can be scaled up in a focus and context fashion, with the additional screen space being used for showing more details. This is another way in which the visualizations behave responsively by adapting to size and aspect ratio. Cells at a larger level of detail can then also allow for providing direct editing facilities. Among others, the available visualizations comprise bar charts, star plots, parallel coordinate plots, or also node link charts. By flexibly providing these as embedded representations in the matrix, analysts can access all the different details of the network. This flexibility is also one big difference to existing work providing embedded visualizations for matrices, such as LiveRec, SAME, or time cells.
As Tom just mentioned, our responsive matrix cells also allow for directly manipulating data attributes. This can be done by either typing a new value or dragging a mark. Effectively, this enables analysts to quickly correct data values or run what-if scenarios, all without the need of switching to a different view or even application. The question now is how all these concepts work together, both on a global and local level. To illustrate this, we will give you now a short tour through our prototype by exploring a soccer dataset. The graph consists of 95 nodes, which are the players. They are characterized by over 30 attributes. An edge exists between two players if they have played for the same club during their career. The edge weight corresponds to the number of same clubs. Here, we are sorting the matrix by the player's club affiliation and select the attributes, appearances, minutes played, total shots and goals for the similarity calculation. What we can see now is that two players are quite prominently standing out in the similarity part, Lionel Messi and Robert Lewandowski. The two lines, with many reddish cells, are indicating that they are dissimilar to most other players, while the green cell at the intersection means that they are similar to each other. To study this pattern in more detail, we create a meta cell by selecting a subgraph around the green cell. We can now see the specific attributes of the respective nodes leading to the similarity encoding. Scaling up the responsive matrix cell adds axis labels to the chart. Via a quick axis menu, we can also change the visualization to get a different perspective, for example to a parallel coordinates plot. However, for now we want to specifically compare Messi and Lewandowski and switch to a unit cell setup. In the central unit cell, we can see that Lewandowski and Messi have the exact same number of appearances and roughly the same shot-to-goal ratio, although Lewandowski has played more minutes. By loading additional attributes to the chart, significant differences become visible. For example, Messi has twice as much ball possession and twice as many touches as Lewandowski. Let's have a look at the relations between them and see if they have played for the same club before. We can directly switch the responsive matrix cell to the adjacency part of the matrix. As indicated by an empty right unit cell, Messi and Lewandowski have never played together. To get a more intuitive representation of the connections, we can switch to a meta cell with an embedded node link diagram. Through interactive highlighting, we can find out that a path between Lewandowski and Messi exists in the subgraph via Thiago and Dembele. Looking at the red line for Messi, we notice multiple nodes that are particularly dissimilar to him. To take a closer look at them, we create a new unit cell selection. When switching to the star plot representation, we can see that multiple values are missing. To fix these, we enlarge the cells further. Now, we can access handles that appear at the marks in the visualization. These allow us to edit the data value and update it to a correct one by simply dragging a handle or entering the value directly. During the editing, the star plot is updated on the fly, as are all other visualizations depending on the edited value, including the similarity part of the matrix. Afterwards, the analysis session can be continued seamlessly by defining new responsive matrix cells in the matrix. Using the prototype you just saw, we conducted guided hands-on sessions to receive early user feedback with 4 PhD-level researchers. 2 of them were interaction experts and 2 visualization experts. These sessions were held remotely via video chat with screen sharing and lasted around 1 hour. Participants received a short introduction and a demonstration of the prototype. Then they were asked to interact with the prototype and test the usability of its functionalities. While all participants agreed that initial training is required to understand both the dataset and the visualization approach, they quickly adapted and applied the techniques without larger problems. They indeed started to explore and reason about the dataset on their own. Feedback-wise, participants rated the experience very positive. They stated that unit and meta cells were indeed helpful for understanding the details. They also thought that being able to switch responsive matrix cells between adjacency and similarity is neatly bringing together the two worlds of structure and attributes. Editing and the immediate feedback was perceived as useful, especially for understanding the influence of attributes in the similarity measure. Difficulties occurred only when observing editing effects with larger responsive matrix cells, as they reduce the visibility of the remaining matrix. As illustrated by our live demonstration and the user feedback, We believe that responsive matrix cells are a promising solution for analyzing complex multivariate graphs. They enable workflows that seamlessly go from overview to detail to editing, offer a flexible definition of what, where, and how detailed information is shown, and are based on well-known concepts including focus and context, semantic zooming, direct manipulation, and responsive visualizations. Our responsive matrix cell approach shares limitations with these base concepts. Responsive matrix cells depend on the ordering of underlying rows and columns, and our focus on context technique causes distortions of the base visualization. To address these, we integrate options to sort the matrix and provide coordinated highlighting between responsive matrix cells and the matrix. We believe that our approach can also be an interesting foundation for future work. For example, it may be promising to consider spatial aspects, such as embedding maps into responsive matrix cells for geospatial networks. Editing could be improved by allowing absolute or relative changes of groups, or providing guidance by indicating reasonable values. Also, more elaborate evaluations should be conducted to compare our integrated responsive matrix cells with classic multiple view approaches. For now, you can check out our online demo as well as our project website for more details. And with that, we thank you for your attention.